Welcome! Today we're going to break down two of the most fundamental concepts from multivariable calculus, curl and divergence. These are the awesome tools that let us really understand how vector fields behave in 3 dimensions.
So to kind of get our brains warmed up, let's start with a question you might not have thought about before. What do a whirlpool and a fountain actually have in common? I mean, sure, they both involve water, but they describe motion in completely different ways, right? One spins around and the other shoots outward. And yeah, that's exactly what curl and divergence measure. Think of it like this. For any 3D vector field, its derivative kind of has 2 main behaviors. You've got its spin, which we call the curl, and its spread, which we call the divergence. So the whirlpool is our perfect picture for curl, and the fountain is our go-to for divergence.
Okay, so let's start with the spin. How in the world do we mathematically describe that whirlpool-like rotation at any single point in a field? The answer? It's the curl. We figure it out by taking what's called the cross product of the del operator, which is basically just a vector full of partial derivatives, with our vector field. Now, the result here is super important. It's not just a number, it's a whole new vector. The direction of this new curl vector tells you the axis the field is spinning around, and its length tells you how fast it's spinning.
So how do we actually compute that cross product? Well, the standard way, and what you see here, is to set it up as a 3x3 determinant. Now, I know this can look a little scary, but it's really just a clever trick, a way to organize all the pieces and make sure all those partial derivatives land in exactly the right spot.
All right, so that's rotation covered. Now let's talk about the other half of the story, expansion. If curl is all about the whirlpoolness, how do we measure the fountainness of a field? For that, we use divergence. The calculation feels similar, but there's one huge change. Instead of a cross product with that del operator, we take the dot product. This gives us a scalar. Yep, just a single number that tells us the rate of flow out of a point. If it's positive, the field is expanding, like a source. If it's negative, it's contracting, kind of like a sink.
And check it out, the formula is way more direct. You just take the partial derivative of the first component with respect to x, add it to the partial of the second with respect to y, add that to the partial of the third with respect to z. Boom, you're done.
Okay, enough theory. Let's get our hands dirty and make this stuff concrete. We're going to apply these formulas to a couple of actual vector fields, just like you would on a problem set.
First up, let's find the curl. We're on the hunt for the rotational properties of this specific field, which could be spinning differently all over the place.
Okay, let's walk through this piece by piece. For the I component, we get negative xy. Now, for the j component, and listen up because this is where everyone gets tripped up, remember the rule for determinants means we have to subtract this whole piece. So that extra negative sign flips things around, giving us a positive 2x. And finally, the k component works out to yz minus x squared. We just put those 3 pieces together, and there's our final curl vector. All right, awesome. Let's switch gears and tackle a divergence example. We're going to find the expansion for this new field, which has some exponentials and trig functions thrown in just for fun. So we just follow our simple 2-step process, right? First, differentiate each part with respect to its own variable. The first piece with respect to x is e to the x sine of y. The second, with respect to y, is negative e to the x sine of y. And the third, with respect to z, is just 1. Now for the easy part, add them all up. And would you look at that? The 2e x sine y terms completely cancel each other out, leaving us with just 1, a constant divergence of 1. Isn't that wild? It means this pretty complex-looking field is actually expanding uniformly everywhere at the exact same rate. Okay, this is where things get really cool. Now that we have a feel for both operations, what happens if we do one right after the other? Is there some hidden connection between the spin and the spread? So let's ask a very specific question that actually uncovers this really deep truth about vector calculus. What happens when you combine these operations? Like, what if you take the curl of a field first, and then you take the divergence of that new vector field you just made?
Yeah, I know. At first glance, this looks like an absolute nightmare, right? We're plugging the general formula for the curl right back into the divergence formula, and it expands out into this long, ugly chain of second-order partial derivatives. But here's the magic trick that makes the whole mess just disappear. There's this amazing property called Clairaut's theorem. All it says is that for most well-behaved functions, the order you take partial derivatives in doesn't matter. Differentiating with respect to y then x is the same as x then y. And because of that amazing theorem, if you look back at that crazy long expression,
you'll find that every single term has an equal and opposite partner. They all cancel out. Every single one. It all goes away. The divergence of the curl is always 0. Now, this isn't just some neat math party trick. It tells us something incredibly deep about how the universe works. It means that if a field is all about pure rotation, if it's the curl of some other field, it can't have any sources or sinks. The whirlpool has no drain and no faucet. The water just spins around forever.
So the big takeaway here is that curl and divergence aren't just abstract formulas for your calculus homework. They are the actual language we use to describe how fields behave. For instance, the fact that the divergence of the magnetic field is 0, that's just the mathematical way of saying that magnetic monopoles don't exist. This is the language of fluid dynamics, of electromagnetism, of weather patterns. It's how we find the hidden spin and spread in the invisible forces that shape our entire universe. Thanks for watching.